Just it is especially the revision lecture that what you have gone through the MSc classes and just a higher one. So prerequisites of Riemannian geometry. Actually, this is the abstract of the course that we shall introduce the basic geometric objects of Riemannian geometry to provide some background. That is a definition of Riemannian manifold. It's the concept of distance in a Riemannian manifold and the groups of isometries with some elementary properties, and emphasis will be given on examples including surfaces and Lie groups. So we'll also just one. So now, first of all, we assume that we have the concepts of differentiable manifold of dimension n, which is denoted by m to the power n. And we know that it is a topological space whose each and every point has a neighborhood homeomorphic to the open subset of Rn. So this concept is known to us, differentiable manifold of dimension n. And it has a structure, smooth structure. So I'm not going to the details of these definitions. We have the concept of tangent space. I think you have the concept of tangent space and also the concept of vector field. Okay. And the cotangent space, which is denoted by T star PM, and the forms, one form, two form, R form. So the concepts are, I think it is well known to you because in post-graduation classes, you have gone through it. And very important concept is one parameter group of transformation, and which is a mapping from phi r cross m to m defined by phi tp, and which also form a group. This is a very important as it is a r cross m. So it is a one parameter group of transformations. If it is r cross m, then it will be a two parameter group of transformations. So these concepts, I am assuming that these concepts we have in our mind. Next one, that is pullback map. Pullback map F star. Okay. So F star is a mapping from this TPM to FPN, and when F is a mapping from M to N, M and N are two different differentiable manifolds of different dimensions. And then we can have the F as a mapping from M to N. Then F star is the pullback map, which is the mapping from FP to F of P. Next, we have the concept of linear or causal connection. Causal is from France. And this causal connection, it is a del from chi-m cross chi-m to chi-m, and denoted by in this way, del x, del y x. It is the covariant derivative of y along x, which satisfies these four criteria. Del x y plus z equals to del x y plus del x z. These four criteria are very important. So if any connection, if any this del satisfies all these four conditions, then we call them as a linear connection. We have also the concept of torsion tensor field, Txy equal to this one, del yx minus del xy minus the bracket xy, and the curvature tensor field Rxyz equal to this one, second order derivative. The curvature can be obtained from the second order derivative of these vector fields. So these are the well-known concepts we have in our mind. Now, from here, we are just starting a little bit more rigorous, that covariant derivative of vector field and tensor field of type 0s. If y is a vector field, and then del yx, I have just told that it's a covariant derivative of y along x. And if x can be expressed as ji del xi, because del xi are the basis vector of chi-m. Del xi are the basis of chi-m. So any vector x can be expressed as a linear combination of this So x can be expressed in this way, y can be written in this form, where xi and eta j are the functions, differentiable functions, the members of Fm, the set of all differentiable functions denoted by Fm, and its local representative, local representation is like this. These local concepts are very much useful in mathematical physics and in applied sciences. So this is a expression for the covariant derivative of y along x. Now, if P is a tensor field of type 0s, that is, if it is a covariant tensor of rank s, then del xp x1 x2 xs, because P is a tensor field of type 0s, so it will act over the s vector fields x1 x2 xs, and it is defined in this way: xp x1 x2 xs minus this way. So this is the expression for del xp. Now, covariant derivative of a tensor field of type 0s, it is called covariant derivative of a tensor field of type 0s along x. If y is a vector field and its components are eta I, then in local form, it del yx denoted by eta I, comma j, and it is actually the covariant derivative of the contravariant vector eta I. Okay, and this expression is this one. Now, just remember that this gamma I jk not Christoffel symbol now, because now we are in differentiable manifolds. On differentiable manifolds, this gamma I jk are the functions of Fm. This 1 minute. This gamma I jk are the members of Fm. Okay. So if we consider this del y del xj along the basis vector, we write in this way: eta I comma j del xi, and the expressions can be obtained easily just by using the definition of del, the 4 conditions of the previously mentioned. We can find the expression. We have obtained the expression for omega. We have obtained the expression for omega in this slide. In the next slide, we have obtained the expression for omega. See, omega is a one form, so we can write it in this form: omega I dxi, because for the forms, the basis vectors are dxi. Okay, for these are the basis vector of this for the forms. So for it is one form. So this is the expression. If I write in this way, omega k comma j, then by del x omega y, we can write x omega y minus omega del xy by the definition of covariant derivative of form. And if we consider this vector field as x as del xj and y as del xk, only the basis vector, if we consider along the basis vectors, then if we put it in this way, we are getting the expression. We are getting this expression. Which is actually the covariant derivative of covariant vector. Okay, so it resembles with that one. Now, generally, del xf is denoted by xf for all f belongs to fm and x belongs to chi m. Now we are coming to the Riemannian metric. So these are the some basic preliminaries of the differentiable manifolds. Now we come to the Riemannian metric. Now, Riemannian metric is a bilinear mapping from chi m cross chi m to fm, where gxy is greater than 0, it is positive definite. Gxx is 0 if and only if x is a null vector, it is called a non-singularity condition. And gxy equal to gyx is symmetric. So M and G is called Riemannian manifold. Now, for existence of G, that is important. For existence of G, M should be Hausdorff and second countable. To get the metric, the topological space should be Hausdorff and second countable. Otherwise, we can't get the metric, because we have two very important theorems with us. That first theorem is that a differentiable manifold M has a differentiable partition of unity. I'm coming to what is partition of unity. A differentiable partition of unity if and only if every connected component of M is Hausdorff and second countable. So I'm not going to the proof of this thing. The proofs are lengthy and it is almost topological part. So it is given in Brittle and Clark differentiable manifolds in chapter 3. So if anyone is interested, you can look into the book, this book. Now, this is a very important theorem for us, that for a differentiable manifold M, which is Hausdorff and second countable, has a Riemannian metric. So this theorem gives the existence of the Riemannian metric, which is for a topological space which is Hausdorff and second countable. Now, what is partition of unity? Partition of unity, I'm just given the sketch of the proof here. The partition of unity means you know that these two conditions will hold. If there is some differentiable functions on some open neighborhood V alpha, and F alpha belongs to Fm, and F alpha is greater than or equal to 0, and F alpha equals to 0 for the complement of this V alpha closure. Okay, this is a closed set. So F alpha is 0 here, F alpha is 0 here, and generally F alpha is greater than or equal to 0. And the second condition is that F alpha P, the summation, is equal to 1. So that's why it is called partition of unity. So say F1 may be 1/3, F2 may be 1/3, F3 may be 1/3, like that. So summation will be 1. And in each neighborhood, in each V alpha, if we take the inner product in this way, then GUV is defined with this F alpha P UV alpha. So in this way, we get the Riemannian metric on a Riemannian manifold. So this partition of unity helps us to get the Riemannian metric. GUV equals to summation F alpha P UV, this F alpha. So clearly GUV satisfies all the condition of Riemannian metric. The three conditions, we can easily verify that G alpha, it satisfies all the conditions of Riemannian metric. Now, the next one, we have to go very fast because in one class, we have many things to review. That if del G equal to 0, del is called metric connection. Okay. And generally, for the basis vectors, G of del Xi, we write it as Gij. And if we break by the definition of the forms del Xg Yz equal to Xg Yz minus G del Xyz minus Gy del Xz. And generally, for metric connection, del G equal to 0, that means the left-hand side equal to 0. So we have this relation, Xg Yz equal to G del Xyz plus Gy del Xz. Now, a space is called symmetric. If space is called symmetric if torsion equal to 0. Torsion equal to 0 means del Yx minus del Xy minus Lie bracket Xy equal to 0. That means this will happen. Del Yx minus del Xy equal to the Lie bracket Xy. So if a linear connection on a Riemannian manifold is symmetric and satisfies the condition of metric connection, then del is called Riemannian connection or Levi-Civita connection. Okay, this is called Riemannian connection or Levi-Civita connection. The Levi-Civita is a student of Riemann, a German mathematician Riemann. And the Lie bracket of XYF, we don't know, it is XYF minus YXF. I'm coming again afterwards. Now, there is a fundamental theorem of Riemannian geometry that every Riemannian manifold admits a connection. It is a unique Riemannian connection. That is important. Admits a unique Riemannian connection. So here to prove, we have to prove the existence of them, show it is a Riemannian connection and uniqueness. So three things we have to prove in this theorem. So this is a fundamental theorem of Riemannian geometry. And this del is defined in this way. This del is defined in this way, 2g del x del y xz equal to in this way. So anyone who is in this, that how it is coming, you can follow the book of Riemannian geometry by Tucard. Okay. Now these conditions to be verified, and we can we going to the details of this. The three conditions can be verified here. Now we have density, that is Rxyz plus Ryz plus Rzxy equal to 0, and in local form it is given in this way. And this is the Bianchi second identity. It is the covariant derivative of R, and the cyclically it is moving on. And this is Rxy, G of Rxy Z u equal to minus G Rxy uz. So it is skew symmetric or antisymmetric with respect to the last two vector fields, and it is symmetric with respect to two at a time. So where G of Rxy Zu equal to Gr Zu xy. Now if G is covariantly, we note that G is covariantly constant. That means as del x G yz equal to 0, so it represents that G jk comma I equals to 0. So covariant derivative of Gk is 0. Now there is another concept of Einstein manifold. That is generally we write G R xy z u equal to R dash xy z u, and if we contract by putting x equal to EI, where EI is an orthonormal basis, EI is an orthonormal basis of TPM, then R dash R EI YZ EI is denoted by SYZ. This is a Ricci tensor SYZ. It is 0 to tensor field. 0 to tensor field, covariant tensor field. And if we put Y equal to Z equal to EI again, then we denote this one by R. It is a scalar curvature. Scalar curvature, Riemannian manifold. So after contracting the first and last, we are getting Ricci tensor. And then again by contracting, that means we are trying to get a something scalar quantity which gives some curvature of the space. So this is the scalar curvature of the Riemannian manifold. And if for a Riemannian or pseudo-Riemannian manifold is that when G is not positive definite. Okay, then we call them as a pseudo-Riemannian manifold. If SYZ equal to lambda GYZ, where lambda belongs to Fm, then the manifold is called Einstein manifold. For an Einstein manifold, lambda equals to R by N. We can easily prove it. Now we can come to another important concept, that is sectional curvature. Now we know that for a surface, for any surface, we know that Gaussian curvature is defined by R1212 by A. This one, where A is the determinant of the fundamental metric tensor, coefficients of the fundamental metric tensors. So R1212 can be written in this form. Okay, because A is the determinant, so that can be written in this form. Thus, for a Riemannian manifold Mn, if we consider a two-dimensional subspace of TPM, if we take that two-dimensional subspace of TPM and denote it by pi, and two linearly independent vectors x and y at P, then K can be defined. This K can be defined in this way: minus Rxy xy gxx gyy minus gxy square. keeping in the mind with this one. Now this is called sectional curvature of Mn at P relative to pi. So from here we can write r dash xy equal to in this form minus k of this for xy belongs to pi. Now since the above relation is true for arbitrary vectors x and y, we can write r dash xy z equal to minus k. Now if I replace this xy by z, so here we are replacing this all the two xy is same and then other xy is by z, we are getting this way. So we are getting g of rxy z equal to this form k gyz gxu minus gxz gyu. So for sectional curvature, rxyz can be written as k gyzx minus gxzy. So from here we can have the source theorem that if at each point of a Riemannian manifold Mn n greater than 2, the sectional curvature of the manifold is independent of the section chosen. It is constant throughout the manifold. Now, result 1 is that a Riemannian manifold of constant curvature is an Einstein manifold. It is very easy to prove, and you can easily prove it. A Riemannian manifold of constant curvature. It is a Riemannian manifold of constant curvature. That means this condition will hold. Is an Einstein manifold. We can easily prove it. Now, is the converse true? The answer is no. That only three-dimensional Einstein manifold is a manifold of constant curvature. Only three-dimensional Einstein manifold is a manifold of constant curvature, and it is also easy to show. You can easily find it. Now, another question is that when an Einstein manifold is a manifold of constant curvature. So this is a very important query, that when an Einstein manifold is a manifold of constant curvature, and it is just you can try to find it. Now I come to the concept of Lie derivative. Lie derivative, that let x and y be vector fields on M. The Lie derivative Ly of x this way is the vector field defined by this way. It is the ddt of alpha t star yp. That is the pullback. It is the pullback map. Okay, where alpha t is the flow on x. It is the flow on x, or that is a one parameter family, and alpha t star is alpha minus t star. Okay. So this is the alpha t star yp is actually this one. Tp alpha minus t y of alpha tp. Now, given any point P belongs to M, there is an open neighborhood U of P and epsilon greater than 0, such that for minus epsilon cross U, alpha t is a flow in U. It is a local one parameter group of transformation. It is a local one parameter group of transformation, alpha t. So alpha t star yp belongs to TPM. It is belongs to TPM, and this T to alpha t star yp is a C infinity curve in TPM, okay, whose derivative at t equal to 0 is Lxy p. This one. This is the actually, so derivative at t equal to 0. Now, in general, if x belongs to this one, there is a vector field, tau 1, 0, m, and p is a tensor field of type Rs, then the Lie derivative is general. It is general that Lx pq ddt of alpha t star pq. So this is the Lie derivative, concept of Lie derivative, the definition. Now, if xy are vector fields and omega is a one form, then Lxf y equal to del x y equal to xf. So for function, when f belongs to fm, Lxf and del xf are same, that is xf. And its local form is this one. It is a local form, Lxf equal to del f del xi xi. Now for two vector fields, this is actually Lxy is the Lie bracket of xy. And locally, this is the expression is this one. Del y del xj xj minus del xi del xj yj, this one. This is a locally, this is the expression for Lxy. And for one form, this is the local representation. This is the local representation. Now we come to the concept of Lie group. The concept of Lie group. Let Ga be a differentiable manifold. It is a differentiable manifold. If G is a group itself, and if the mapping mu G cross G to G defined by mu AB in this way, and the inverse map I G cross G defined by IA equal to A inverse are both differentiable mapping, smooth mapping, then G is called Lie group. So these two operations, this mu AB equals to this multiplication AB and this map I, the inverse one, they are both differentiable map, then G is called Lie group. And it is named after Norwegian mathematician Sophus Lie, 1842 to 1899 AD. So an example is that GLNR, denote the set of all non-singular n cross n matrices. So GLNR is a subspace of MNR, which is a set of all matrices of n cross n, and GLNR is a set of all non-singular. That means determinant of A. That means determinant of A is if A belongs to GLNR, then determinant A is not equal to 0. Then determinant. And if we define that for A matrix A, phi A equals to in this way. So there are n square component. So phi GLNR to Rn square is the homeomorphism. And this is a n square dimensional differentiable manifold. GLNR is a Lie group. It is a Lie group. Another good example is that if G equal to R, and if we define phi AB as A plus B and IA equal to minus A, then is R with these operations is an abelian Lie group. This general linear group we denote in this way, general linear group GLNK, where K may be R or C. So this one, A is a n cross n matrix and determinant A is not equal to 0. We call it as a K Lie group, where K may be R or C. K may be R or C. The group law being the multiplication of matrices, the group law. Similarly, SLNK, it is a special linear group where determinant A equal to 1. Okay, determinant is 1 is a closed normal subgroup of this GLNK, and it is a special linear group. It is called special linear group. Now another good example is K orthogonal group. K orthogonal group. This is A also belongs to GLNK. Sometimes it is written in this form, GLNK, or sometimes it is written in this form also, GLNK. So if A is a matrix whose determinant A is not equal to 0 and belongs to this one, and A transpose A equal to I, the orthogonal condition, orthogonality condition. If this holds, then it is called K orthogonal group. It is called K orthogonal group. So these are all the examples of Lie groups. Another example is this one, very important group, is that if S is 0 I minus I null matrix, actually this is a identity matrix, and it is minus I, and the analogous group is called SPNK, and such that A belongs to GLNK and ATSA equal to S. If it happens, if this holds, then it is called K symplectic group. Okay, it is a K symplectic group. Now UN, it is another unitary group. This is also an important concept. UN, where A is GLNC. A belongs to GLNC. It is the complex linear group, complex general linear group. And this one is a conjugate transpose of A. If this holds A bar T equal to A, then it is called unitary group. It is called unitary group. For example, we can consider this one. Here, I consider A in this way. A is taken as minus I, 2 plus I, like that. 2 plus I minus 2. We take case A1. Okay. And this one will be your minus I bar minus 2 plus I bar 2 plus I bar at this 0 bar. So if the product of this equals to I, then it is a unitary group. It is a unitary group. Now see, this is a very important concept that if G is SL2R, SL2R is your, this one, SL is SL2R. It is 2 dimension and K is R, SL2R, special linear group. Okay. If it is SL2R, if G is SL2R and M is SO2, SO2 is giving afterwards the definition. Actually, it is a very important concept, so I've given here. Then the quotient space G quotient M is actually the hyperbolic space H2, the dimension of two-dimensional hyperbolic space H2. The quotient group is G and M is SO2. What is SO2? SO2 is this one, special orthogonal group. SO2 is a special orthogonal group with A belongs to the orthogonal group and determinant A is also plus minus 1. And it is the subgroup of ONK. It is also a Lie group. It is also a Lie group. And so this is a very important concept that the quotient space G, quotient M is a hyperbolic group. And hyperbolic group XY belongs to R2 and Y greater than 0. And the metric is given in this way, metric ds square equal to dx square plus dy square by y square, metric on H2. Remember that UN is not a complex Lie group. Okay, it is actually real subspace of all Hermitian matrices. So it is not a complex Lie group. Now, this is another important concept that Riemannian manifolds as a metric space. Riemannian manifold as a metric space. The distance is a very important concept on Riemannian manifold, which is defined as follows. Let Mg be a Riemannian manifold. Mg is a Riemannian manifold now. Okay. Now, given a piecewise smooth curve C from AB, the closed interval AB to M, the length of C is denoted by this integration A to B root over G C dot dt. Okay. For each pair of points X, Y in M, we define. So this is the length. This is the length of C. This is an important concept, and you know this one. This concept is known to us. Now, for each pair of points X, Y in M, we define dxy. Dxy, how we are defining? That infimum of the lengths of all piecewise smooth curves. We are considering all piecewise smooth curves and we are taking the infimum of the lengths of all piecewise smooth curves starting from X and ending at Y. So remember, so note that if C is a geodesic, then C dot is a constant one. It is always constant because this is a fixed one. And LC will be, if you integrate this one, it will be B minus A root G, this one. So this is the, if C is geodesic, then LC will be this. Now, the result one, given a Riemannian manifold, Mg, the function D is a distance on M, and the topology of the metric space MD is the same as the manifold topology of M. Okay, so the topology for the metric space MD and for the M are the same. And then result two, any geodesic minimizes the length between any pair of sufficiently near point on it. Conversely, any curve having this property is a geodesic. So these are some basic results can be obtained. You can find it in the book of Base's book, Einstein manifold. Now there is a very important theorem that is called Hopf-Rinow theorem, and there are various versions of this Hopf-Rinow theorem. They are German mathematician Hopf and Rinow. So I am giving one version, and then I will discuss on some other version. For a Riemannian manifold Mg, the following conditions are equivalent. What is the conditions? Mg is complete for the Levi-Civita connection. MD is a complete metric space. The bounded subset of M are compact. The bounded subsets of M are compact. So these three are equivalent. So in other way we can say that if Mg is a complete connected Riemannian manifold, then any two points can be joined by a geodesic. So it is another form of Hopf-Rinow theorem, and the proofs are very lengthy. You can see any book or any notes, lecture notes. I will mention afterwards. So, and these properties imply that these three conditions imply that for any 2 points xy in M, there exists at least a geodesic starting at x and ending at y. So what I've told just. So, but this D doesn't imply ABC. So that is important. These ABC are equivalent, but D doesn't imply ABC. So it is written separately, that's why. D does not imply the completeness of Mg, and there may be many more than one geodesic connecting x and y. And another concept from here can be obtained, that a compact Riemannian manifold is complete. A compact Riemannian manifold is complete. There is another important theorem which I have not mentioned here, Peter-Bell theorem, that any compact Lie group G is isomorphic to a closed subgroup of UN. Any compact Lie group G is isomorphic. Any compact Lie group G is isomorphic to a closed subgroup of UN. Closed subgroup of UN. Now I come to another concept, that is the diameter. The concept of diameter of a Riemannian manifold. It is the supremum of the distances of any 2 points in M. So this is the supremum. Distance is the infimum of the all lengths, and diameter of the Riemannian manifold is supremum of the distances of any 2 points in M. Now, what is a ray? A ray, respective a line, is any infinite geodesic defined in C from 0 to infinity to M, maybe from minus infinity to infinity to M, such that for any 2 points xy on C, any 2 points xy on C, the distance dxy is exactly the length of C between x and y. Okay, so this is the definition of ray. Now, there are again an important theorem that if Mg is compact, the diameter is finite, and there exists x and y in M such that dxy is the diameter. And if Mg is complete non-compact, the diameter is infinite. If it is compact, the diameter is finite. And if it is non-compact but complete, diameter is infinite. For any x in M, there exists a ray, and there exists a ray C with C0 equal to x. So for complete non-compact one, there exists a ray C. Now we come to the Riemannian immersions, isometries, and group of isometries. What are they? Now let MNG and NMH, two different differentiable manifold or pseudo-Riemannian manifolds of different dimensions. I want to mention that there are different dimensions. M is of dimension n and n is a dimension of M with the metric G and H. A smooth map F from M to N is a pseudo-Riemannian immersion if it satisfies F star H equal to G. F star H, so pullback concept is here, F star H equal to G. If it satisfies this concept, F star H equal to G, where F star is the pullback map of M and N less than M. N, the dimension of M is less than N. Equivalently, we can write in this form also. If for any x in M, the tangent map TXF satisfies H TXF, H TXF y, H TXF x, and this one is equal to GXY. So the distance between the two tangent vectors at N is equal to the distance between the two tangent vectors at M. So that is the main concept of that it is a pseudo-Riemannian immersion. Now an isometry is a pseudo-Riemannian immersion which is also a diffeomorphism. Now I think you have the concept of diffeomorphism. For Riemannian manifolds, there is a characterization of isometrics which involves distances. Now a surjective map F from Mg to Nh between two Riemannian manifolds is an isometry if and only if it preserves distances. dH fx fy equal to dg xy. So this is a surjective map, and dimension of M and N now will be same. Otherwise there will be immersion, but for isometry it will be the dimension should be same. So dH fx fy equal to dg xy. Now the composition of two isometrices. So we have the isometrices. So this one is the F is called the isometrices. So the composition of two isometrices is an isometry. And for any isometry F, the inverse diffeomorphism F inverse is also an isometry. So they will form a group. So composition of two isometry is an isometry, and the inverse is also isometry. So the set of all isometrices from a Riemannian manifold Mg into itself, okay, now it is M to M, forms a group. We call it the isometric group of Mg. It is the isometric group of Mg and denoted by IMG. So IMG is the set of all isometrices from M to M. Now, the important example is that all translation is an isometry. In RNG, n-dimensional Rn, and G is a usual metric, any translation is an isometry. These are the example. Okay. We can verify easily. The isometric group of a two-dimensional sphere. The isometric group of two-dimensional sphere. I think in the advanced courses you can how to find this the isometric group. You can learn. The isometric group of a two-dimensional sphere is the orthogonal group O3. The isometric group of the Poincare disk model of the hyperbolic plane is the projective spatial unitary group. So these are the examples of some isometric group. The basic result on IMG is the following theorem given by Mayers and Sternrod in 1939. What is that? That let MG be a pseudo-Riemannian manifold. The group IMG of all isometrices of MG is a Lie group. So IMG becomes a Lie group and acts differentiably on MG. I'll coming to the action on a Lie group, act differential on MG. For any x belongs to M, the isotropy subgroup, it is called the isotropy subgroup if fx equal to x holds. If fx equal to x holds, then we call them as a isotropy subgroup of IMG. It is called isotropy subgroup of IMG. If MG is a Riemannian manifold, IXMG is a compact subgroup of IMG. That is very important one. Moreover, if MG is compact, IMG is also compact. If MG is compact, then IMG is compact. These remarks have given, some remarks have given by S.T. Yao in 1977. So these are the another thing. IMG acts properly on any Riemannian manifold MG. So it is acts on MG. IMG may be compact even if MG is non-compact or non-Riemannian. IMG may be compact even if MG is compact, then IMG is compact. But if IMG may be compact even if MG is non-compact. And dimension of IMG is less than equal to n plus 1 by 2. So these are proved by S.T. Yao. With equality holds only if MG has constant sectional curvature. So if MG has constant sectional curvature, then this is equal. Then less than equal to will be equal to if M is constant sectional curvature. Since an isometry preserves G, it preserves Levi-Civita connection, geodesics, volume element, different types of curvature, that is sectional curvature, which is curvature, scalar curvature, Gaussian curvature, all the things are preserved by the isometries. Now I come to some other concepts of Lie group, that left and right translation on Lie group. For any A belongs to G, G is a Lie group. A mapping ALA from G to G defined by LAX equal to AX is called a left translation. So it is acting from left. So it is called left translation on G. Similarly, RA from G to G is defined by RAX equal to XA is called right translation on G. Now set of all left and right translations on G form a group also. So all these things will form a group. Now left invariant vector field and right invariant vector field. So a vector field X on a Lie group G is called a left invariant vector field on G if LA star X equal to X. LA star, you know, that is, it is the differential map of LA. LA star X equal to X or RA star X equal to X, where LA star is differential of L. So that means it's remain invariant like that. So it is called left invariant and right invariant for this one. If X and Y are left invariant vector fields, then Lie bracket XY is also left invariant vector fields. You can easily show it. So it is an exercise for you. Now, let tau be the set of all left invariant vector fields. Let tau be the set of all left invariant vector fields on a Lie group G. If xy belongs to tau and bc belongs to R, LA star bx plus cy equal to b. So linearity condition holds for LA star and LA star xy equal to LA star x LA star y, and it will be xy. So thus bx plus cy belongs to tau and Lie bracket xy also belongs to tau. Thus, tau is a vector space and it is called Lie algebra over R. Now, what is the definition of Lie algebra? Lie algebra is defined in this way, that just Yes, Lie algebra is, I just write it here. That it is a Lie algebra is a vector space over R with a bilinear map. There is a bilinear map from V, suppose V is a vector space over R, V cross V to V given by xy as xy. So leave bracket xy. And which satisfies two conditions. The first condition is xy equal to minus yx, and second one, it satisfies the Jacobi identity. It satisfies the Jacobi identity. So these are the two conditions to satisfy for Lie algebra. Now note that the behavior of a Lie group is determined mainly by its behavior in the neighborhood of the identity element E of G. So this is very important theorem. There is that the Lie algebra tau of the Lie group G is isomorphic to the tangent space TEG at the identity element E belongs to G. So this is a very important theorem, that it is isomorphic to the tangent space TEG. Now, invariant differential form, a differential form omega on a Lie group G is said to be left invariant if LA upper star omega LY, omega LAP equals to omega P. It is called left invariant form, left invariant differential form. LA star omega equal to omega. Similarly, for the right invariant, I have not written in the right invariant. Now, there are some exercises you can work out that if omega 1, omega 2 are left invariant differential forms, then show that d omega, omega 1, wedge omega 2 are also so. A differentiable form omega on a Lie group G is left invariant if and only for every left invariant vector field x on G, omega x is a constant function. So these are the two exercises you can try. Now, set of all left invariant forms on G is an algebra over R and denoted by tau star. If tau is a Lie algebra of a Lie group G and tau star is the set of all left invariant forms on G, then d omega xy equal to minus half omega Lie bracket xy, where omega belongs to tau star. This is the Morey-Carter equation. Now, I just within 2 minutes, I will conclude that one parameter subgroup of a Lie group. Now, let a mapping F from R to G given by Ft from Ft be a differentiable curve on a Lie group G. And if these conditions hold, Ft Fs equal to Ft plus S, then the family Ft is called a one parameter subgroup of G. And let H be a one parameter subgroup of a Lie group G, then H is a commutative subgroup of G. We can easily prove that H is a commutative subgroup of G. And if X is a left invariant vector field on G, then prove that it is complete. So this is the little about one parameter subgroup of a Lie group. Now, action of a Lie group on a manifold. A Lie group G is said to act differentiably on a manifold M if the following conditions are satisfied. For each A belongs to G, there induces a transformation on M, that is P is mapped to PA, and AP from G cross M is giving a PA in M is a differentiable map, and PAB equals to PAB for all AB belongs to G. So this is called G acts on M on the right. So as A is coming on the right, so it is acting from the right, and if A comes on the left, it will come from the acts on the left, from the left. There is an example So let G be a GL2R and M is an R, and F is a G cross M to M, be a differentiable mapping defined by in this way. So it is G cross M. Actually, it is from M cross G, because this is coming. It is from P. M is the element here. If the element of M is here, and the element of G is here. Oh, no, sorry. So G, the element of G is this one. Okay, the element of G is this one. So all right, G cross M to M, and it is defined in this way: AP plus B, and this is an action. F is an action on M. Now, lastly, we just give an example of isometric surfaces. Now, let S1 be a surface of revolution given by the parametric equation this way: y1 equal to u1 cos u2, y2 equal to u1 sin u2, and y3 equal to a cos hyperbolic inverse u2 by a. This is a surface of revolution, equation of surface of revolution, and whose metric is coming to this one. His metric is coming to this one. And S2 be a helicoid. S2 be a helicoid with equation this one: y1 equal to v1 cos v2, y2 equal to v1, and this is y3 equal to a v2. And the metric is given by this. It's coming from here. The metric is coming from here. Now, if we set v1 equal to this one, root over u1 square minus a square, and v2 equal to u2, then the two surfaces have the same matrix. So if two surfaces S1, S2 be such that there exists a coordinate system with respect to which the line element on S1, S2 are characterized by the same metric, then these surfaces are said to be isometric. Okay, they are called isometric. So the transformation of the parameters is called isometry. The transformation of the parameters is called the isometry. So this is the rule of isometry. Now, a surface which is isometric to Euclidean plane E2 is called developable surface. It is called developable surface. We know that any mat can be rolled out as a cylinder. So cylinder is a developable surface. Cone are developable, but sphere, torus are not. They are not developable surface. So a surface which is isometric to Euclidean plane E2, it is called developable surface. And for Euclidean plane, we know that the Gaussian curvature is 0. For Euclidean plane, the Gaussian curvature is 0. So for developable surfaces, the Gaussian curvature is 0 is the necessary and sufficient condition. So this is all the revision done about some Riemannian geometry. Okay. And so thank you all for listening.